Okay, last one. We're going to do something called a comparison test. Okay, this has a lot to do with taking something you don't know a lot about, but maybe you know that it's related to something else. And then, so like for example, if you, I think it's simple. No, I'll just show it to you. I can't think of a good non-math example off the top of my head. Okay, this is the kind of math sense that you need to have, a number sense, a sense of what's bigger and smaller, especially as you look at denominators. Okay, so we're gonna just quick throw some inequalities on here. So if you compare 1 over x and 1 over x plus 2, they're both hyperbolas. They both have asymptotes. X plus 2 is moved in what direction? Okay, moved 2 to the left. All right, which one has the bigger denominator? Always, no matter what you plug in, if you compare the two. X plus 2, the denominator will always be bigger. Since its denominator will always be bigger, what about its overall value? It will always be smaller. Okay, so if the overall value is always going to be smaller, then you want to put your inequality in there that's going to be like that. 1 over x will always be larger than 1 over x plus 2. Now I know these are two pretty easy functions, but if you had your preference of which to integrate, which one would you prefer to integrate? 1 over x, right? It's the easier one to integrate. Okay. All right. Next two, these are inverse square functions. So their graphs also look similar. Both branches of these graphs is where a hyperbola would be diagonal branches, one branch in quadrant 1, one branch in quadrant 3. These graphs are both in quadrant 1 and 2. They're both upper branches. It's just this has been moved 2 to the right. Okay, so which one has the larger denominator? X squared. So since it has the larger denominator, its overall value will always be smaller. So then the inequality has to go that way. Okay, and in this case, which one would you prefer to find the antiderivative of? 1 over x squared. That's easier to find an antiderivative of that. Okay. All right, when you look at e to the x, knowing which one is going to be always have a larger value. Okay, we're not talking about denominators here. We're just talking about exponentials. And all exponentials are big. But one of those exponentials is bigger than the other. Okay, which one? The one with the x squared is going to be the larger value. So we have that. But which one would you prefer to integrate? E to the x. Okay. And then in the final case, we have e to the x, which is another exponential, but it's going in a decay. Okay, it's decreasing. And so by virtue of decreasing functions, then the negative one is going to be a smaller value. So it's this way. E to the x negative x is always going to be larger than e to the negative x squared because it's getting smaller as we go. And we'd rather integrate e to the negative x. Okay, so thinking about those relationships, you're going to use preferential integrals. Say, I really don't want to integrate that one. I'd rather integrate something that is either larger or smaller than it, and I'd rather integrate that because it's easier. This is called comparison. When you exchange one function for another, assuming that their behaviors are pretty much similar, they behave in very much the same direction. Their graphs have very similar behavior, and so you can do what's called an integral comparison. All right, so this is called the integral comparison test. Without actually integrating the given integral, you can, because it's not easy, okay, that's the point here. It's not an easy integral to integrate. You could compare it to one that is easier. And depending on the relationship, you can say a couple guarantees. All right, in our definition in the green box, they have defined f of x as always the smaller function, and they've defined g of x as always the larger function. If that is the case, if you can prove that the smaller function converges, which means it narrows to something, if the smaller function converges will depend on whether or not the one that was larger than it converges. So you can assume that f of x converges if g of x converges. Sometimes they call these squeeze tests. All right, can you picture it? Okay, if you've got two functions that are coming down like this, and red is always bigger than green. Okay, so red is always bigger than green. But red is easier to integrate than green for whatever the defined function is. If you can show that that red, because it's converging, it's squeezing down to a value, and we'll be doing this with dx as our x-axis, so we're squeezing to the x-axis. If you can show that, then you can assume, because of the relationship with this one being lower, it will also converge. Okay, so if a bigger one converges, then the smaller one will also converge. Okay, vice versa is true as well. If you flip that, and you say they're going the other direction, and you've got this one, and then this one, okay, if you can prove that this one diverges and grows without bound, it has to force the one that's bigger than it also to diverge. There's no way for this one to turn the corner and come back down if it has to stay larger than one that is also increasing. Okay? Now, what this doesn't say is the converse. Okay, what if you can show that this one, the larger one, diverges? If you can show that, are you guaranteed anything about the lower one? No, because this one could turn around and still be lower, but you're not proving, it's not being squeezed to anything. It kind of has the mind of its own. The same thing is true the other direction. If you show that the larger one, the smaller one converges, doesn't mean that the other one is going to converge either. So be careful that you're proving the right direction. You can only prove if the larger converges, then the smaller must converge. Or if the smaller diverges, then the larger one must also diverge. The if is kind of in an awkward place. I kind of wish it was the other way around. If the larger converges, then the smaller must converge as well. If the smaller diverges, then the larger must diverge as well. All right, let's just practice it. Does this one converge or not? Well, that's hard to integrate. And so we want to instead compare to the integral of 1 to infinity of e to the negative x instead. Do the one that is easier to integrate. So we start with the assumption that the relationship in terms of inequalities between e to the negative x and e to the negative x squared. Which one did we say was the bigger one again? Which direction should the inequality go? Okay, this one is bigger, so start with that. And then if that's true, then compare the integrals of both of them. So since the function relationship is established, the integral relationship is established, because integrals just mean area. And if you're saying the function's always bigger, then the area always has to be bigger as well. And then focus on the easier one. So the easier one says, okay, I'll do this side. I'll say b is approaching infinity, so I'll go 1 to b, e to the negative x dx. So that's going to be the antiderivative of negative e to the negative x plus c going from 1 to b. That one's going to be negative e to the negative infinity plus e to the negative 1. which is equal to what value? 1 over e. So I have shown that the bigger side converges to 1 over e. What that tells me is that the smaller side must also converge. It does not tell me that it converges to 1 over e as well. It just tells me that it also converges to something. The behavior is what's preserved, not the actual number. So since 1 to infinity of e to the negative x dx converges, then 1 to infinity of e to the negative x squared dx also converges. But what you have to be careful about not saying is that they converge to the same number. They do not converge to the same number, but they do both share convergent properties, the property of convergence. And that only works because you proved it for the larger one. Okay, here's another one. What would you compare this one to? So the function rad x, x to the 6 plus 1, what would you compare that to? What would you rather do instead? Well, what do you want to take off? First of all, what makes it hard? The plus 1. Okay, so let's say I'd really like to compare it to that. Without the plus 1. And then what is that value? What is the square root of x to the 6th? X cubed. So that's the one that you want to look at. You want to look at x cubed. All right, which direction does the inequality go? Which one has the larger denominator? So therefore, which one will have the smaller value? The original is what? Smaller. So we're like that. Okay, so since that relationship is established, then we want to investigate what kind of behavior this equation has. All right, so that's what we're going to investigate. So we'll set up an integral, negative infinity to infinity of x to the negative 3 dx, which has to be split because it's improper. So we've got to split it at 0 minus, and then we have to split it again at 0 plus. And then this is the same homework that you did last night. We're just trying to figure out, what does it do? Does it come out to an actual number where it converges, or does it end up to be infinity and does it diverge? And then we keep going. All right, I'll replace my limits. My limit as a approaches negative infinity. So a is going to 0 negative, x negative. In fact, I'm going to just jump right to the antiderivative here. So negative 1 over x, negative 2 over x squared plus c, going from a to 0 minus. And then on the other one, we're replacing the top one. So b, and we'll get negative 2 over x squared plus c from 0 plus to b.